Hello. How's everyone doing? Are you enjoying PyCon so far? Well, let's welcome Pamela McANulty to tell us more about multiprocessing in Python.
Good afternoon. Hello, everybody. My name is Pamela, and we're going to talk a little bit about multiprocessing. Weird. How do I get this thing moving first? There we are. So who am I? I'm a senior developer at Cloud City. We're a contracting company. I'm also the bass player in a band called Girl Skull, or Girl School, depending on how you want to pronounce it. And my Twitter handle is PMcAnulty01. I've been doing Python for about 19 years now. I started in 2000. Mostly web work, but done a lot of data analysis, some IoT work, and some other cool stuff. So, framing the problem. This is a quote that I saw a couple years ago, and I love it. It really describes almost all of the multiprocessing stuff and thread work. You know you need to do something, you need to use the resources, and just things don't work the way you want them to work in surprising ways. Multiprocessing, or Python processing, comes in a lot of different flavors. So there's the main one, which is one process only, and that's just you use the dunder main function, and you write your script in it, or your app, and it runs, and you're great. And you don't have to worry about all the intricacies of trying to use multiple servers and dancing around and making sure that things work together and don't collapse and collide with each other. And then there are threads, and threads seem like a great thing, except that Python uses a global interpreter lock. So you really don't get a second CPU very easily. Threads basically allow you to write very straightforward synchronous code that all blocks each other unless you're doing an I/O, some kind of I/O. And it's really it's really hard to remember, what's going to do an I/O, what's not going to do an I/O, what's going to give up time, what's not. It can get very confusing. And that's one of the reasons that async I/O came along, because I call it shuffling the I/O, because you're starting something and then something else gets to work on. You're just constantly having these mental threads of execution that are sharing things, sharing the CPU when somebody's not, when another thread is waiting for something. But it's very explicit about when you're giving up time and when you're not. So although it can be confusing, it's a little easier to figure out. You have to think. It forces you to think about how things work together. Now, if you really want to use multiple processes, there's this multiprocessing module comes with this thing called pool. And it allows you to literally map a function to some kind of iterable. If we're chunking each one piece, gets one piece of data, and you get the resulting changed data back. And that's really good for some basic things where all the data is the same. And especially if you're doing something that's going to get run once, come to the end, start over again. And then if you've gotten bigger, you can do third-party tools. You can use, you can move to a queuing system like Redis, or ZeroMQ, or something built under Kubernetes. There are a lot of tools that you can use to scale up in different ways. But what I'm going to talk about is the things that you need to do if you want to use the multiprocessing process function or class. So when do you want to use multiprocessing? The number one thing is when you're CPU constrained. If you're trying to churn through something, and you're not waiting on the network all the time, and you're not writing to disk or reading from disk all the time and not blocking, and you just want to use all the CPU cycles you can, and you can split up your work into chunks, you want to use multiprocessing, because that way you're using all, you have these CPUs, you go into AWS, 1,000 CPUs, you run Python with one, you're kind of spending a lot of money that you don't need. The other thing is sometimes you have situations where you want to use the OS's data, the OS's process protection model, where you're using some kind of third-party library that you don't trust, or you're using some data that you're doing something where you are a little worried about security. This way, you know that process A and process B won't be able to talk to each other or overwrite each other. Other times, connection or operational integrity. So I use a lot of SQL alchemy. It's not a big fan of having multiple threads using the same transaction. You can do it, but it's hard in one process. So it's a lot easier just to break them off and to have each process have its own database connection. And the last thing are sometimes you have library limitations where it's just not thread safe at all. You want to do things that even if you want to use threading because it's mostly I/O bound, but your library is not thread safe, you need to use something like multiprocessing. So I'm going to talk. My examples are going to talk about using the queues and what you need to do. But I have this complex, what I call my complex multiprocessing example. And this came out of the project I was doing last year at my work, where we were working on an IoT device that was sucking in data from two different sources, sending it off to servers, central server, but also needed to be able to get commands from the external servers and recognize some unusual events, and that all had to synchronize together so that you weren't, there were places where you wanted to make sure you serialized things and places where you didn't. So I have the main process. So my architecture was I had a main process that listened on an event queue. I mean, how often have we heard an event queue this weekend? I mean, everything talking about async I/O, twisted, etc. And that basically it takes events, processes them, and depending on what it does, it'll either send it to what I call the send queue, which gets serviced by a process that sends stuff out, or it's dealing with a reply, some internal request. Main process has dealt with it, and the reply and the listen process will take care of it. So one of those sources is what I call the status subprocess. We have all these IoT devices, and things can go wrong on the device itself. It can run. You might not know. Might be running out of memory. You might be getting disk errors. The network might be getting flaky. You have no idea why there. Why am I only getting connections half the time? I want to see what's happened over time. Why is my wireless disconnecting, and I come back a couple hours later? So this is monitoring the system environment. And then the observations. This was the core reason for the product in the first place. It was hooked up to an HVAC system, and it would track temperatures and airflow rates and power rates and dozens of other parameters, many of which were raw numbers that needed to get calculated somewhere. And rather than send these raw numbers and do all the calculation on the back server, we were doing them here. And that's why we were using the CPU work here, because the status process was constantly kicking off subprocesses to do work. But this thing would take the data, and it would spend, depending on the data, 1 to 2 seconds to do to convert it to a common format and do the math, taking these raw register values and turning them into cubic feet per minute, or temperature ranges, or whatever, or power levels. Send queue, we're sending data to the servers, and I don't want to have to worry about, I don't want to think about it anywhere else. You queue it up, the data server says, okay, I'm going to send it to this, send it to the central server. If the network's down, I don't want to break everything else. So that send subprocess would manage a queue, manage its own internal queue to disk, but also just have an in-memory queue that worked out nicely. And then the last one was, sometimes you want to go tell that system to go do something. There was a listen subprocess that would listen on a socket. When it got something, queue up an event to go do something. The main process go do something, and then it would come back through another queue. So main process. This is the point: is that it's a complicated system. It's not all doing one thing. It's not. There are different kinds of data. They need to talk to each other. There are places where you want to make sure you do things synchronously. So if a reply comes in that's going to be accessing some system, I don't want to be having some other system trying to access that at the same time. So there's a coordination involved. So that's just some background to give you an idea of what a complicated system is, and I might refer to it a couple of times here, the rest of the talk. But the main thing is I have 5 tips. Tip number 1, and this is the one that's most multiprocessing related, is don't share data. First of all, you can't share Python objects across processes. Just imagine what would happen if the garbage collector tried to run against something that some other process was dealing with. And on top of that, when you share data, you have to manage the locks yourself. And that doesn't scale. So pass messages. It makes your code, you break your product, break your process and your architecture into as small bytes as possible, send them to queues, and have people have processes. I anthropomorphize my computers all the time, so I'll refer to them as he, she, them, whatever. Have them work through have each process do what it needs to do by reading and using its work through a queue. So one other rule is make sure each queue only handles one type of message. There's a little exception I'll talk about in a minute, but it's really complicated if you have a queue that gets multiple kinds of messages, and you have then the subprocess that's reading from that has to know, okay, is it doing this? You have to have this if statement everywhere. And if you're already breaking things into multiple processes, don't do that way. Do it at the queuing level. And also, each process should be reading from one queue at a time. Only be listening on one queue. It gets very confusing if you're saying, okay, is there anything here? Nope. All right, here. Now you're doing a kind of a select on a set of sockets, and that's not worth it, for queuing system. And one of the great things about using multiprocessing queue is it ships. It's part of the standard library. That means that, but it's also a queuing system so that when you want to get big, if you do get big, or if performance becomes a major bottleneck, you don't have to rewrite your architecture. You just have to encapsulate the queuing up, your queue gets and puts, and put them and use Redis or RabbitMQ or some other queuing system that will work for you better, more consistently. The downside about queuing is that it uses pipes, and every message, every piece of data is pickled. So pickle is not the fastest. There are some risks. Make sure that you're not, if you're sending something that uses one import and it's not, like date time, if it's not available, it can break in another subprocess. In general, try to keep your messages away from anything more complicated than a straight dictionary. So a couple of examples. Setting up a queue is pretty straightforward. You can set up a queue that will use up all the memory it can use, or you can say only accept 5 messages, and then if you try to put something on that queue, it'll block. Putting stuff on a queue is pretty straightforward. Getting something off of a queue, becomes very important in one of the other tips, but always use a timeout. And closing a queue, for a long time I thought I just had to close them. Turns out you have to wait for its associated thread because it's a pipe. The thread, every queue when you create it, creates a thread that manages the data through the pipe. Because the pipes can fill up faster than the queuing system. Tip number 2, always clean up after yourself. I bet most of your parents told you always clean up after yourself. I bet your partners probably tell you that too sometimes. I know mine does. In multiprocessing, there are 2 parts. One, you need to make sure that everybody knows that they're done. When do you clean up? When do you clean up until you get done? And the other part is they have to clean up after themselves. And the last part is the master process has to clean up everybody else. That's the mom who cleans up any mess that's still lying around. So I use 2 different ways to notify processes. I have a signal. And this is a place where it's a kind of a shared memory, but it's just a flag that says 1 or 0, and you can wait on it. And I use an end message so that when I get a signal that it's time to shut down, I queue up a message that just quote end, unquote. And when you're reading a message, when you're reading from a queue, if you see a message that says end, it says, oh, break out of my loop. Because every one of these, when you're reading from a queue, it's just a loop. Get the next job. Get the next job. Processes, as I said, and main process is mostly concerned with shutting down the subprocesses and cleaning up the queues that it knows about. So this is what a standard subprocess loop looks like. It's got wait for the event to set, if it's set, go, leave, break out of the loop, read the queue, and then if the item I've got from the queue just is simple end, break out of the queue, but break out of the loop. So that's most of what happens in a process. You look for the signals that say, I need to stop, break out of your loop, do a little cleanup, leave. Main process is a little harder when it's shutting down. What we do is we set the event. It's probably already set, but you might not be. You're never sure. So set the event to hope that somebody else is that anybody didn't get the message will. Then you wait for some time to wait. I usually say 3 to 5 seconds. Wait for all the threads to try to shut themselves down cleanly. Wait for them to see the message, take the time. This code here says wait for up to whatever my stop wait seconds is right now. And then it says, okay, join this sub-process, in timeout if I time out after n number of seconds, the total number of seconds. And if it finishes early, I just keep recalculating how long I've got, so I will never wait longer than 3 seconds. And if I get to the end of that, I think we have problems. So as long as I keep a list of the processes I've started, and I basically pop it off the list, and if it's still alive, because it's possible that it finished up between the time I gave up and the time time I'm looking at it now. If it's still alive, send it a terminate. It's going to kill it. It's going to kill it hard. It's going to wipe it out. You want to log that. I'll talk about that later. And then if it isn't alive, get its exit code, because you want to know whether it exited cleanly or whether it died for some other reason. So again, when you're as part of shutdown and cleaning up queues, you probably want to drain them. If you've queued up a whole lot of things when you're shutting down, nobody's going to be consuming stuff out of those queues. You're going to want to drain them. If there's something important in there, draining them might do a lot more work than this. It might take the item and store it somewhere so that when you start up again, you'll have some process that says, okay, preload the queue with all the old stuff. And the last part, as I said, always join the thread afterwards. So what happened with me was especially when debugging, it's like Control C, fine, it closes, and then every other time I would get this exception message. Why am I getting an exception message saying that there's a thread broken or something like that? And then finally, after reading docs and figuring it out, it's like, oh, my app is shutting down. I'm trying to get out of, the main function is gone, but there's this one thread that's still hanging around because there was it never got a chance to tell that it's done, or there was still some piece of data sitting in a queue that it had to clear off. So that join thread is something just removes a spurious error. If you're queuing very large objects, in the course of megabytes, that join thread might take a little while because it's going to have to drain the queue. Drain the pipe, rather. Tip 3, just like driving, obey all signals. And I know some of us here from Boston, like I am, and obeying all signals is not primary in their nature. But so every process, both the master and the sub-processes, need to handle, and here it says both term and int signals. Today, in Lynn Root's talk earlier, I realized, there's hup, and there are 3 or 4 other signals that you want to be able to handle that might shut you down more gracefully or reload the configuration. It varies. Each signal, the way the algorithm that I use is my signal handlers say, I'm going to set the shutdown event. The first 2 times I get that signal. The 3rd time I get that signal, I'm going to raise an exception. That way, you can test, if I do Control C and when I'm debugging, the first time through, it's not going to throw a keyboard exception. It's just going to do a normal shutdown. Nice, clean shutdown, get to practice it. But if it's stuck, Control C, Control C, Control C, and now I'll get exceptions, and I can test failure modes, and just keep myself from being stuck. Because you really want to make sure that one of the key things with multiprocessing is you want to shut everything down cleanly. You don't want to leave connections open. You don't want to have zombie processes around. And what I have found is if you can shut down cleanly, you've probably thought about all the race conditions you need to do. So shut down, set the event the first 2 times, third time raise. And sometimes you might need to go in and change some system settings when you have a brain fart. I don't remember now, so I'm just going to skip it because I got to keep going. That's the rule. Okay, so signal handlers. This is pretty straightforward. I create a signal object that I can pass into the handler, so it knows it has a clue what's going on, and that object is where I track how many signals, how many times I've had the signal, and I also pass it the shutdown event, so it knows how to set that event. Tip 4: don't ever wait forever, ever. In multiprocessing, if you have something that says, "Oh, it'll only take a second," it's going to take a year someday. If you say, "Oh, I don't know how to do that, it's too hard," work to figure out how to do it. Because there's some interfaces that don't have a timeout mode or something, but really try your best. It makes it a little more complicated, so no process should ever get stuck. Every loop needs to be able to terminate. Blocking calls need a timeout. And timeouts are basically, how long can I wait before I have to start shutting down? If I can wait 2 seconds before, so that if I've got 100 processes, and I can wait 20 seconds or 30 seconds. Okay, make your timeout 2 seconds. Probably want to be under half a second. And okay, you're going to poll, but timeout. And if you have something that doesn't time out, it doesn't take a timeout, you're going to have to write it yourself. You're going to write the. So nice thing, queues, tell it to block, but you can give it a timeout. There's a nice 1/100th of a second timeout. If it's empty, which will come back as empty in the timeout, then just keep going. Sockets, I can set the timeout when you start up with a socket. In fact, for 0MQ, you could actually set the timeout on the socket when somebody was waiting on it. So I ended up, when I was using that tool, I ended up setting the timeout in the signal handler for that process. Made the code a little easier to read. I don't have an example here, but sometimes there is no timeout. There's I just have to get it. I can be blocking or non-blocking. Then make a non-blocking call. If it comes back empty, sleep for however long that is, or half or whatever that is, and just go check again. It's not pretty, but you have to make sure that you're never sitting in a spot that you'll never get out of. And last, and this is one everybody knows, but report and log all the things. Use the Python logging module, because that's what you should use. There's some problems with multiprocessing, and so that what you really want to do is you want to set up another subprocess or even a thread, but probably a subprocess that has a queue, and your logging function writes your logging message to that queue, so that one process can keep them in line. Because if you don't, then you might get that garbage that they quote from the screen. The other trick is to make sure every log message tells you how long it's been since the application got started. You can put a timestamp in there, but then you're always going to be doing mental math of, was this a half a second or a quarter of a second? You're going to, you've got 12 decimal places or 6 decimal places. You're going to have to do this mental math when all you really care about is started at 0. This thing happened at 0.04. This happened at 0.05. Make sure that you name each process in the log so you know where it came from. You can give your process ID, but you won't know what that is later. You have to log every exception, every error, include tracebacks, preferably record something that you consider a warning. You ought to log things like during the startup and shutdown routines, because that's where things get really nasty, and also whenever certain significant events happen. In the complex case, when a request came in an external request came in, we would log it. And whenever one of the status or the observation requests came in, but we didn't log everything that got sent to the servers. And in debug mode is where you put an enormous number of log statements. You just log everything, because you're looking for, okay, how do these two, you're going to look for how these two processes are interacting. Is one happening a little faster than you expect? Is one blocking in a way that you don't expect? So this is my how am I going to log something? I use monotonic. I don't remember anymore exactly why, but when I looked through, it was the one that was consistent, and it was not going to get changed very easily. And then just my F strings, they're the best, and tell me how many hours and seconds it's been since we started, and then the name, and then whatever the message is. And here's some sample, just okay. What process is it? What's the user? How long that first numeric column is how long it's been since I started. So you can see it starts up pretty quickly and gets going, and everything's more or less linear. Then I tell you what process it is. It's a worker process or is it the master process? And then some steps then a description of what's actually going on. And shutdown, you can see I hit the Control-C, and oh look, normal shutdown went through. It was great. Last, in conclusion, we'll just repeat these things. There are 5 things, good tips. Don't share always pass messages. There are times when you have problems where your messages are enormous. Then that's a little beyond the scope of this one. There are problems like C. Titus Brown tells a story about how he would have a data structure that was a sparse array that was on the order of 50 to 100 gigabytes larger, and there was no way he could distribute that. People kept saying, "Oh, figure out a way to put it across bunches of different computers," and you can't because everybody was writing to that array and reading from it to figure out epigenetics. Always clean up after yourself. Handle term and int signals. Obey all signals. Don't ever wait forever. And report and log all the things. Some of these are straightforward. The only one, as I said, the only one that's really multiprocessing related is don't share. Use messages. But all the rest are things that every time I've tried to write multiprocessing stuff in my 20-year career, these are the things that drive me crazy. That okay, what's going on? Oh yeah. So as part of this talk, I actually wrote a blog post for my company, read a lot from the programming guidelines section, and also I have a little library package that wraps, because most of this stuff is boilerplate. You just have to figure it out every time. So I've got a module that more or less wraps multiprocessing to handle queues, to group up processes, to handle shutdowns, and has an encapsulated framework for worker queues, worker processes, so that you can use the default startup and shutdown functions and things like that, and pass basic data. My name's Pamela McANulty. My email address is sort of on there. My Twitter handle is pmcAnulty01. And how much time do we have left? Do we have time for a question? Am I wrong? Have I sped up?
It's up to you. We have about 2 minutes.
At least one question, I guess.
All right.
And as Brandon says, please ask your question in the form of a question.
How do I convince my coworkers who are used to using Java that Python's multi-threading, multiprocessing business is not the worst thing ever to walk the earth?
Well, it's not the worst thing ever to walk the earth.
That's what they think, though, and I can't convince them.
But compiled systems tend to be, if they're comfortable with that, it's going to be more performant. Unless you're counting developer time, in which case they're writing in Java. I mean, and my first manager, the one who introduced me to Python, says Python is a competitive advantage because it means my developers can do more work faster.
Well, let's thank Pamela for a great talk.
Thank you.
Thank you all for coming, and keep enjoying PyCon.